Hi and welcome to MSc. In this video we're going to be looking at solving exponential equations, specifically an algebraic method called change the base. So to understand what change the base method is, we're going to look at a couple examples to work through this. So the first example here is fairly simplistic, and many of you will look at this and know that 2 to the power of 3 is 8, therefore x has to be 3. But I want to use this as an example to illustrate how change the base method works. So what we want to do in this case is rewrite 8 as a base that is the same as we see on the other side. So I can say that this equation then, we could say 2x is equal to, and I can change this to write it as 2 to the power 3. So we have changed the base, rather than this being x to the power 1, which we don't write the 1, we've now changed the base to match. And if we have same bases on both sides, only one factor on both sides here, the only way this can be true is if the exponents are equal. And in this case, we get x equals 3. Now, in this easy example, we probably already knew that to begin with, so why would we go through this type of hassle? Well, this is the method of change the base, and when we get to more complex examples, then we'll see its value even more. So over here in the second example, I see I have 16 to the power of x minus 3, and I have 4 to the power of 7x. We're trying to find x. We're trying to find out what that is. Now this would be very difficult to do by trial and error, and we can certainly get ones where we wouldn't be able to do it by trial and error. And so I want to change the base of these so that the 4 and the 16 are actually written with the same base. So certainly we could change them both to base 2, but base 4 is probably fine to work in because I know that 4 squared is 16. So we can rewrite the 16 here as 4 squared. And that is then raised to the power of x minus 3. Now on this side, I'm not going to change this base. Again, changing them both to a base 2 is fine. It just makes yourself have a little bit more work. And you can even try that as an extension exercise if you'd like. We know the power of a power rule says when an exponent is raised to another exponent, they multiply. In this case, though, we need to be careful because this 2 multiplies the x and multiplies the negative 3. So on the next line, we're going to write 4 to the 2x, and we're going to say negative 6. And all of that is equal to 4 to the 7x. At this point, we have one factor on each side. They both have the same base. And so the only way that this is equal, we can say, therefore, the only way that's equal is if this exponent is equal to this exponent. And now I have a relatively simple equation that I can rearrange and solve. I'm going to move the 2x across, and it's going to become negative on the other side, minus 2x. So I'm going to get negative 6 is equal to 5x, right? And then I'll divide both sides by 5 to move it across. And the 5's, of course, cancel on this side. And I'm left with x equals negative 6/5. Again, very hard to probably do that reasonably by trial and error, but there we've done it, and we've utilized this change the base method. We changed the 16 to match the base 4. Much like we did here, we changed the 8 to a base 2 to match. Probably wasn't necessary in that first example. Let's look at a couple more examples to continue to explore this process. So here's an interesting example here, because we see 7 to the x squared, so we have a square root of a square, like we have exponents of an exponent here, and that's okay. But we have a 1 on this side. And so I know I'm trying to change the base, probably to match the 7, but it's a 1. And so any 1 to any number is just 1. But what we can remember here is when we have 0 exponents. So we're not going to change this side here at all. But on this side, I can say that the 1 is the same as 7 to the 0. And so that's a common little trick that you'll see in these types of problems. And so the only way this is true, we can say therefore that we have to have the exponents be equal to one another. And of course then we can move the 4 across the equal sign. And then we can take the square root of both sides. And we're going to get the plus minus of the square root on this side. So we can say x is going to equal plus or minus 2. And we were able to solve this as well. This might be one you could maybe do by inspection, but again, you can imagine more complex or involved questions that might not be possible, but you still might need to use this power of 0 to get a 1 value trick. So we'll end this video with this last example, which looks sizably more complicated. And there's a couple pieces I want to draw your attention to as we go through this and utilize some different exponent laws. So we know we're going to change the base. It looks like probably base 5 is going to work well. I see this 1/5, and another trick that you'll see in these types of problems is utilizing the negative exponents. So I can rewrite 1/5 as 5 to the negative 1. And then I'm still going to have the 2x minus 2 as my exponent. I know 25 is 5 squared, and that will be 3x plus 1 remains as my exponent. And on this side, we do need to know our exponent powers, probably up to products of about 1,000, seems to be fairly common for both international baccalaureate and advanced placement courses. So we know here that 5 to the power 4 is going to be 625. And we keep the 3x as the exponent. Again, change the base method won't always work. If we have bases where we can't change them to be alike, then we have to use some other algebraic method, perhaps logarithms. We also need to know our powers of common bases fairly well for this process to work. So here now we're going to do the same thing we did a couple examples ago, where this negative 1 is going to multiply both of these, this 2 will multiply both of these, and of course that 4 will multiply here. So we have some work to do. So we're going to say this is 5 to the negative 2 plus 2x plus 2. This is going to be then times 5 to the 6x plus 2. And this will then be 5 to the 12x. Okay, so we see we have common, we've done the change the base piece. They're all common, they're 5s. But there's 2 factors here and 1 here. So we have more work to do. If you remember when we multiply like bases with exponents, we add the exponents. So we're going to do that here. We're going to say that this is actually 5 to the negative 2x plus 2 plus this exponent, which is 6x plus 2. And all of that is going to be equal to 5 to the 12x. So I can simplify this. This negative 2x and this positive 6x, that's going to make 4x. And the plus 2 and the plus 2 will also make a positive 4. And I'm left with the 12x on this side. Now I can drop my bases and I can say therefore that 4x plus 4 has to equal 12x. And we're going to collect like terms. We're going to write 4 is equal to 12x minus 4x. So we have 4 is equal to 8x. I'm going to bring my work back up here. And I'm going to divide both sides by 8. So it's going to be 4 eighths is equal to x, which of course we can write as x equals 1/2. So we were able to solve this rather complicated looking problem by using the change the base method. We had to do some different rules, but if you can do this type of complex problem, you're probably good to go with this method, regardless what they throw at you. I hope this method has been helpful. I hope this video has been helpful, and as always, thank you very much for listening and watching.